Hello, once again we come back and proceed in our lessons of calculus, and in our last lecture we spoke about the notion of the indefinite integral, and we said that this notion means that we are searching for antiderivatives of functions, or in fact we can say that the antiderivative of functions are no more than integrals, but they are indefinite integrals in the sense that they don't give a number like the definite integral, but they yield a function of x. And these function of x, when you differentiate it, you get the function, the original function. In other words, that integrals of this sort, which are indefinite, they are antiderivatives, or you can say that the antiderivatives are indefinite integrals. And these indefinite integrals, when you differentiate them, as I said, you get the original function. The only drawback with this, to consider these sort of integrals or these antiderivatives as integrals, the only drawback is that you have, this applies only to functions that are continuous or having an antiderivative. And in fact, this is not a major drawback because you encounter continuous function in all sorts of applications, and this is why what you really you can really apply your fundamental theorem all the time, and you can say that since you are applying your fundamental theorem, then you are really considering antiderivatives as integrals. And these antiderivatives, we should be able to calculate them, and this is why we shall proceed to state some methods of integration. Usually differentiation is much simpler, right? Because differentiation, there are no such complicated methods of differentiation. Any function you can differentiate it based on the chain rule or whatever method you use. And there are, as I said, there are no books, it's called books of differentiation, but there are books of integration because usually when you come to integrate a function, as we said in our lecture, it's usually complicated. You have to find ways to integrate functions. In other words, to find antiderivatives. Antiderivatives by themselves are not important. Yani it's not really something fascinating to find an antiderivative of a function. You wish to calculate the antiderivative because you shall eventually use them in calculating integrals or areas beneath graphs. In other words, to apply the fundamental theorem. So in our course towards the fundamental theorem, we should be able to calculate antiderivatives of functions. Now, to calculate antiderivative of functions, the one that we saw in our last lecture were simple ones, but usually come up with others which are a little bit complicated. And this is why the mathematicians try to classify methods of attack, which you can use them, each one for a particular kind of example. So in this lesson, we shall start by the method which is called the integration by substitution, and this is the most common or the most widely used method of integration. Mathematicians, they usually call them integration by changing the variable of integration. Sometimes they differentiate between changing the variable of integration or substitution. In other words, changing the variable of integration applies to a category of functions, whereas in my lesson here, I shall use both, because actually what you do is that you change the variable and you do a kind of substitution, and therefore I'm generalizing both and calling them both the method of substitution. So what you do in your substitution is that you search for another dummy variable. When you locate it or you substitute it inside the integral becomes simpler. And that's the main philosophy. The main philosophy of substitution is that you have a complicated, cumbersome integral, and you wish to facilitate it, to simplify it. How? By searching for another variable. When you substitute into the integral, it becomes of the kind which is much simpler, which you can handle easily. So in this lesson, we shall be first talking about this method of substitution and when is it used, what kind of problems it deals with, and then some common types or forms of integration. And then we are using Leibniz differentials. Again, here, all the time we mention the name of Leibniz, because Leibniz, using his differential, have been able to simplify calculus tremendously. And then we shall speak about some trigonometric integrals. Now, when is it used? Usually it is used when you deal with integrals of this sort. You have here a composite function, the integral of f of g of x. Here we are talking about antiderivative of this particular kind of functions. You have a composition between f and j, and then outside the bracket here you have g dash. So you have f composite function f circular g of x, and then what's inside here gets differentiated again. When you notice that you have a sort of integration of this kind, then you directly know that you are dealing with method of substitution. So the theorem is that what you do is that if you want to calculate the integral of the antiderivative of f of g of x, g dash of x dx, what you do is that you will notice, or you have to integrate small f. When you integrate small f, you have capital F. And after that, as it is written here, if capital F is an antiderivative of a small f, what you do, the integral of this sort, which is a composition between f of j times the derivative of what's inside here, is what? The result is that you obtain, you integrate first small f to obtain capital F, and then you do again the same composition with the small function g of x. And the proof is very easy. All you have to do is you differentiate the right-hand side. The derivative of the right-hand side is equal to what? From the chain rule is equal to capital F dash, which is small f, of u, which is g of x, this is dummy variable that you always introduce, times the derivative of du by dx, what's inside g dash. So you get this expression here. And you don't ever forget the constant c. For example, here you have e, and you want to integrate e to the square root of x divided by the square root of x. This is a form very much similar to the one we have just mentioned. Why? Because here you can take the function small f of x to be e to the power x, whereas g of x is equal to square root of x. Why? Because here you notice that it is a composition between e to the x and the square root of x, and 1 over the square root of x is the derivative of g. The only exception is that when you differentiate square root of x, you get 1 over twice square root of x and not square root of 1 over square root of x. So what you do, in order to put it in a form similar to the one we have just seen previously, you divide by 2, you multiply by 2. Now you have what? This form here is what? Is e to the square root of x, which is f of g of x, times g dash, which is 1 over square root of 2 twice square root of x. So what's the integral? You start by integrate f. The integral of e to the power x is e to the power x. When you integrate it, you do the same composition again with the function g. So what you do here, the form that it's written in this form, and 2, you leave it as it is. This is the constant. And then the result is what? The composition between the integral of small f with the original, with the inner function, which is square root of x. So you have e to the power square root of x. And you don't forget about c. Here again, you have the function f can be taken as sine x. Here you have a composition between sine x and g of x. You have sine 4x cubed times the derivative of what's inside. But the derivative of what's inside is not x squared. It is 12x squared. So all you have to do is you multiply and divide by 12. And this is the form that you have seen before. It is f of g of x times the derivative of what's inside, which is 12x squared. So it's f of g of x times g dash of x, and the integral becomes what? Becomes the integral of small f, which is what is the integral of the sine? It's minus cosine. So you have minus cosine, and you do the composition with what's inside, which is j, and you get cosine 4x cubed. So it's automatically what you do is that you integrate small f, and you do the same composition with the function g. Now, some common forms of integration here. For example, the function f, most of the time we meet a particular value, a particular function of f. For example, f of x, most of the time it's either x to the power n or square root of x or 1 over x. So here we list the same type of integral of f of g of x times g dash of x, except that f is either one of the 3 forms you have here. So here, this one here, you have what? A composition between x to the power n and g of x times g dash of x. So integrate x to the power n. What's the integral of x to the power n? Is x to the power n plus 1 divided by n plus 1. And you search for the composition between x to the power n plus 1, which is capital F, and the same function g of x. So you get this one. And here, we shall not dwell very much on this, because here f is square root of x, and here f is what? Here f is 1 over g of x, 1 over x, I'm sorry, 1 over x, and the integral of 1 over x is ln mod x. So ln mod x is capital F, and you search for the composition between capital F and the same function g, you get ln mod g of x. For example, here you have what? Here you have g of x is equal to 1 plus x to the power 7 raised to the power 100. So you have, f of x is equal to what? X to the power 100. The integral of x to the power 100 is what? Is x to the power 101 divided by 101. And here you have g dash, but this is not g dash. G dash is equal to, g dash of this is equal to 7. So all you have to do, you multiply it by 7 and divide by 7. Now you have the form f of g of x, f is x to the power n of g of x times g dash of x. So what you do is that you integrate x to the power n. What is the integral of x to the power n? Is x to the power n plus 1 divided by x to the power n plus 1. N is 100. So it's x to the power 101 divided by 101. So you have 1 over 700, x to the power 101, and you do the composition with g to obtain this expression here. Again, here is your f is equal to square root of x, and your g of x is x squared plus 1. And this is g dash. It's not exactly g dash. You have to multiply by 2 in order to be equal to the derivative of what's inside. So I can tell you directly without turning the slide what is the integral of this. You integrate the square root of x, which is what? 2 over third x to the power 2 half plus 1, 3 over 2. So it's 2 over 3 times x to the power 3 over 2, and then you take the composition with what's with inside, and you divide by 2 because you ought to have here 2 instead of x only. So we shall see it here. Here it is directly. This is here x to the power 3 over 2. This is the integral of the square root of x. This is f, and you do the composition to obtain what's inside x squared plus 1. Here again, you have f of x is equal to 1 over x, and g of x is equal to x to the power 4 plus 2x cubed. And what's on the numerator here is the derivative of what's in the denominator, except that this gives you 4x cubed, and you have here 2. So all you have to do is you multiply it by 2 and you divide by 2 in order to obtain it in the form of f of g of x times g dash of x. So what you have, in fact, you must have somewhere half. Yeah, that's it. And here your form, this is g, and this is g dash, except you divide by 2 to obtain here 4x cubed plus 6x squared. And the integral of this, it's a form like the one we saw before. Here 1 over x, the integral is ln mod x, and you do the composition with g of x, and you have half ln mod g of x. But then all we have said are correct, except that if we use Leibniz differential, it would be much simpler. And we said before, always I advise the student to use the Leibniz, the dx and dy of Leibniz, and they facilitate so much all your expressions, whether in differentiation or in integration. Now suppose this is our original integral which you wish to calculate, to find, in other words, the antiderivative of this function. What we do is the following. We substitute u is equal to g of x. If u is equal to g of x, what will happen? That du by dx is equal to g dash, or that du is equal to g dash of x dx. So what you do is that you substitute f of g of x to be equal to f of u. And g dash of x dx, look at that. It's as if you multiply numbers together. G dash of x dx, you call it du, and the integral becomes equal to what? F of u du. So look at the simplicity here. Instead of you have a cumbersome integral of this sort, you end up with a much simpler integral that you can easily deal with. And this is the way that you do all the time. And this I'm advising you all the time, the method of substitution here, using calculus of Leibniz, the differential or the notation of Leibniz, facilitate always your integral. For example, this one here. Let's go back to the ones that we saw before. Instead of saying this is f and this is j, and this is j of x, this is the integral that you wish to calculate. All you have to do, you substitute 1 plus x to the 7, you take it as u. So now du by dx equals 7 times x to the power 6, or that you can say that du is equal to 7x to the power or x dx. So what you do, you take this value here, x to the power x dx, here, and you substituted for du divided by 7. Here it is, du by 7. Whereas what's inside here, since you call it u, so you have u to the power 100. Look what we've done in one simple step. We have been able to, using the differentials of Leibniz, to facilitate or to simplify the integral into a form very amenable to integration. This directly is one of the elementary functions, the integral of which you know. What's the integral of u to the power 100? Is u to the power 101 divided by 101. So you get u, and if you wish at the end, and this is actually your result here, if you wish to substitute u for f of x, because you started with the function of x and you want to end up with the function of x, all you have to do, you substitute u at the end for 1 plus x to the power 7, and you get your final expression. And this way is much simpler than the original method of searching for a certain function f and for a certain function j. And not only that, but also it can be used in any form of substitution, not only the one that it has to be put in the form f of g of x and times g dash of x. Now here you have, for example, tan x. What you do, we know that the integral of tan x is sine over cosine. What you do here, we realize that the numerator is the derivative of the denominator. So we substitute u is equal to cosine x. So du by dx is equal to minus sine x, or that du is equal to minus sine x dx. So what you do, you take the numerator with dx itself and you call it minus du from here. This becomes equal to minus du divided by what? Divided by u. What's the integral of that? The integral of that is very simple. 1 over u. The integral is ln mod u or ln u. It's up to you, depending on what applications you are using. And then here, after that, if you wish, you can again substitute for u is equal to cosine x. So you get minus ln cosine x, or you insert the minus in the power of what's inside the u to obtain logarithm, the ln of 1 over cosine u, which is ln of the sec. So you see the simplicity of substitution using Leibniz differentials. Here again, you evaluate, for example, the integral of e to the power x dx divided by e to the 2x twice x minus 1. Here again, you do a kind of substitution. The sort of substitution that you have, actually substitutions, they are not straightforward. You have to search, because here we don't have much time to lose on a particular substitution, and then you found that it doesn't lead you anywhere. So it's a matter of experience. Integration, as a matter of fact, is not like differentiation. Differentiation, there are a set of 3 rules: the derivative of a quotient or of product of function or the sum of 2 functions. But here you have to find the particular substitution. So it depends on the experience. The more integration you do, the more you find the particular easily the kind of substitution which you. So here, for example, we take e to the x is equal to. So you have here e to the x dx is equal to u, so the numerator becomes equal to the u, and the numerator becomes equal to what? U square minus 1. Now you decompose 1 over u square minus 1. It's the difference between these two quotients, and the integration is easy, because the first one is logarithm and the other one also is the logarithm, and you logarithm minus logarithm is equal to logarithm of the quotient of this of u minus 1 divided by u plus 1. So again here it's the substitution using the differentials of Leibniz which facilitates all the steps that you have to do later on. Again here, what kind of substitution you use? You have to look it out here into, for example, either you say we substitute, for example, 1 over x. No, this won't. In other words, you have to contemplate your exercise or your problem. Here you see something. You see that the derivative of this expression here, the derivative of ln x is equal to 1 over x. So actually, it's put in the form of f of g of x. Where is f here? F is 1 over x. And g of x is 1 minus ln x. And the derivative of 1 minus ln x is minus 1 over x. So in fact, this is in the same form we've seen before. So what kind of substitution you will use? You will take g of x, which is equal to, so what is g? Is 1 minus ln x. So this will resolve your problem. So if 1 minus ln x is equal to u, so minus 1 over dx is equal to u, and then you can take dx over x, or this expression here, the quotient dx, divide by x only to call it minus du, and you are left with in the denominator of 1 minus ln x, which you have called already u. So you end up with this integral here, and this is straightforward because the integral of 1 over u is logarithm, and then at the end you substitute for u 1 minus ln x. So it's systematic, the way using differentials of Leibniz. It's systematic what you do. Here, for example, sometimes the integrals are in the form, sometimes you facilitate them by doing a substitution in between. It's not always you have to find one substitution. You may do a substitution to facilitate or to simplify your expression of integral, and then you may have to resort to another substitution. Sometimes you do 2, 3 substitutions. Each time a substitution comes or intervenes, so your expansion or your integral becomes simpler. For example, this one here. If you take x is equal to AU, your integral becomes 1 over A outside, and you have 1 minus u square. But this is an elementary integral that we have seen before in differentiation, and these I'm listing them so that you can go back to them if you wish, but you will find them in many books. Here again, these are integrals of some functions that you encounter sometimes in the literature, so it's worth mentioning them. Now, for example, this one here, you have an integral of this sort. This is not a typical integration or function that we find. So what we do is that you complete the square. But if you put x minus 1 is equal to u, what you get? You get 1 over u squared plus 4 du. And this is, you can look it up in the table directly, and because this is known. You don't have to memorize this. Once you reach here, you look it up in your text and you find that this is the arctan or the inverse function of the tan. These are other examples in which you have to resort to substitution. For example, this one you can complete the square. And this one here, let us complete the square, for example, for this one here. The integral over 1 over square root of 2x minus x squared. How we can deal with this integral, for example? It looks complicated, but it is not. All you have to do is that you can put it in the form dx divided by square root of, here you have minus x, here you have 2x, so you must have here minus 1. Because if you expand this, what you get? You get minus x squared plus 2x minus 1. So if you add here 1, you get 1 cancels out with 1, so you end up with this expression here, which is 2x minus x squared. So how you can deal now with this integral? The x divided by the square root of 1 minus x minus 1 squared. All you have to do is that you can substitute x minus 1 is equal to. So the integral becomes dx is du. So you have here du divided by the square root of 1 minus u squared. What is the integral of this? This, here, you stop here and you look it up in the table, because this is kind of elementary integral, the integral of which is one of the elementary functions. This is the inverse function of the sine. So you say arc sine, or sine minus 1 of what? Of u. Plus, of course, c. And then if you wish, you can go back and substitute for u. The value of u is equal to what? To x minus 1. So you have here x minus 1 plus c. See? And all the other integral is the same. This one, for example, here, you can take e to the x minus 3, because when you complete the square here, you have e to the x minus 3 all square. So you can take this as u, and you proceed later further. Again, there are some trigonometric integrals which you use also substitution to resolve them. For example, here, sometimes you meet integrals of this sort. This is sine to any power. These n are integer powers. Sine cube, for example, or cosine cube, or sometimes you have sine times the cosine, and it is a shame that the student cannot handle these sort of integrals, because, as I said, even in economics, you have behaviors that are cyclic, and there is some turnover between, for example, growth and recession, and these you can analyze them through what is called a cyclic or a periodic phenomena. And these periodic phenomena, the best way to represent them, even if they don't exactly exhibit the behavior of sine over cosine, but there is a scientist at the time of Napoleon in France, and this scientist had been able to prove, or to show at least without proof, until the proof was later on found, that all periodic behaviors can be expressed in the form of sine and cosine. So this integral of sine and cosine is worth explaining them. So when you have, for example, an integration of this sort, suppose, for example, you have n is odd. Suppose, for example, you have here, for example, the integration of sine cube x dx. What you do, you can write it in this form. For example, sine square x times sine x dx. And then what you do, now you want to put it in a form in which the substitution will help you. So what you do, you can substitute sine square by 1 minus cosine square x dx times sine x dx. Now here, directly, you have a form of f and j. How? Because here you can substitute you can substitute cosine x is equal to u. So if you substitute cosine x is equal to u, so what you have here? You have here the integral of 1 minus u square times, you differentiate this, you get minus sine x dx is equal to du, or that the negative sign comes outside, and then sine x dx is equal to u, and you end up with a very simple form of integral. Here you have a function, the derivative of which, in fact, is equal to this function. And in fact, here, it's the form of f of g of x, g dash of x, because you can take, for example, f is equal to 1 minus u square, and the derivative of u is sine, so it is f of g of x, g is cosine, and the f is 1 minus u square, and what's outside is g dash of x. So you try to integrate this one here, and the integral becomes equal to what? Minus 1, the integral is u, and plus u square, which is u cube over 3, plus c, and finally, you can substitute u for cosine, and the integral becomes equal to minus cosine x plus cosine cube over 3, etc. And this is the way how you deal with all these sort of integrals. So when you have here, for example, sine to the power, which is odd, what you do is that you can take out sine, and then this one becomes even. Because it's even, you can substitute for sine square 1 minus cosine square, and you put it in this form here, and this form here is what? Is a derivative of a function. The derivative of cosine is sine, so here now you have f of g of x times g dash of x. G dash is sine, and g of x is you have here the f function is 1 minus u square times n minus 1 over 2, and the g is cosine, and you have here the form of f of g of x. So what you integrate really, in fact, is 1 minus u square to the power n minus 2, and then you do the composition again, if you wish, at the very end, between u and cosine. Now, if n is even, usually you substitute sine square using the twice the angle. We know that sine square x, and we remember in one of the lessons we said that in trigonometry identities, the student should only memorize 3 laws: the sine of the sum, and the cosine on the sum, and sine square plus cosine square is equal to 1. From these 3 identities, you can deduce any form of any other identity in trigonometry. You don't have to memorize only the 3. For example, this one here, you easily calculated using one of the 3 identities. So here, if you have, for example, integral of sine square, you substitute for this expression here, and the integral of cosine 2x is directly sine 2x divided by 2. For example, here, sine to the power 5. It looks complicated, so we'll do this one. Sine to the power 5x dx. What you do here, you substitute, you take sine outside dx, and then remains here what? Sine to the power 4. But sine to the power 4 is 1 minus cosine x to the power 4, because here this is sine square to the power square, the sine to the power 4. And then here directly what you do, it's finished. The integral is finished, because the derivative of cosine is minus sine, so you take cosine x, you take it to be equal to u. So what you end up is what? Here, cosine x dx is equal to u, so you get here minus sine x dx is equal to minus du, so you have here minus. All this, you call it du, and all this becomes 1 minus u square to the power square. So you have here again, with using the Leibniz differential, you have been able to transform your function into an algebraic function in which you directly know the integral. This one gives you u. You have plus u to the power 4 minus u to the power 5 divided by 5. And here you have minus, so you have 2 u to the power square, which is u cubed to the plus c. Is this what we obtained? Exactly, this is what we obtained. All you have to do is that at the very end, you substitute for u is equal to cosine x. When you have sine cube, when you have, for example, two sine and cosine involved together, so what you do is that you can watch out for the power which is odd. Which power is odd? Here, the power of the sine. So what you do, you decompose the sine into a sine and a sine square, and you transform everything into cosine. So sine square becomes 1 minus cosine square, and the cosine to the power 6. And again, here you have a function of cosine times sine. So what's the substitution that you shall use? You shall use a cosine equal to u, and directly when you substitute cosine is equal to u, you get here what? Du, and you get here what? You get here u to the power 6 minus u to the power 8, and you directly can do the integration. When you have, as I said, when you have odd powers of sine or cosine, then you can deal with very easily. But when you have powers which are even, then you are stuck, and you have to use the identities that we mentioned before. You have sine square, you substitute for this bracket, and the cosine square for this bracket. In other words, all these trigonometric integrals of sine and cosine only, or of sine and the cosine together, you have to search for the factor or the one which has an odd power. And from this, it's the beginning of your solution. But whereas here you have square and square, so you substitute for sine square and here for cosine square. You multiply them together to get here cosine square, and then you decompose again the cosine square, and you end up with what? You end up with constants and cosine to the 4x, but cosine 4x, the integral is equal to 1 over 4 sine 4x, and that's your solution. Sometimes you have, for example, a tan function. Like for example, this one, the integral of tan to the power 7x dx. We know that the derivative of the tan is sec squared. So what you do is that you have to find a way, because here 10 to the power 7, we don't know the integral of 10 to the power 7. We know the integral of the tan, which is ln sec. So 10 to the power 7, you can do it this way. You can, for example, say this is 10 to the power 5 of x times 10 squared. But then you substitute for 10 squared, which is sec squared x minus 1 dx. And you write it in this form. 10 to the power 5x times sec squared x minus the integral of the 10 to the power 5x dx. Here you have made a progress. Why? Because you have been able to transform 10 to the power 7 into a 10 to the power 5. In other words, so all you have to do is that you want to know what's the value of this integral here. So, and what about 10 to the power 5? You write it as 10 to the power 3 times, you decompose again, 10 squared, which is sec squared minus 1, and you keep decomposing all the time. And in each time, you only you have to resolve a certain integral at the beginning here. But this is very simple. Why? Because we know that the derivative of the 10 is sec squared. So all you have to do is that you can substitute u equal tan x. So the integral becomes what? The derivative of 10 is sec squared. So sec squared x dx becomes this part here becomes equal to du, and this becomes equal to u. So directly here, the integral is u to the power 6 divided by 6. So what we have here, the integral of 10 to the power 7 of x is equal to what? Is equal to 10 to the power 6 divided by x minus the integral of 10 to the power 5. But then you keep doing the same thing. This is called a reduction process. In other words, you obtain the derivative of 10 to a higher function using the integral of a smaller type of functions. Sometimes, for example, sometimes, for example, instead of this kind of integral, sometimes you have other form of integrals. In other words, this method of substitution, which I called method of substitution, you can say that it's kind of changing the variable of integration. And it's a way of doing it. The idea is that you have an integral, and it's cumbersome integral. It's plenty of variables, and you don't know how to deal with. You are not accustomed to this particular integral. You have a list, and I advise you not to memorize these integrals. You have a list of integrals. All the books that you study from have in the cover the integrals of elementary functions. So you don't have to know them. But the idea is to transform the integral which you deal with to these type of integrals in order to apply directly the result. So, for example, suppose, for example, we take some examples. For example, suppose you have something like this, integral of 1 over x to the power half plus x to the power 1/3 dx. And you wish to find a particular substitution to resolve this integral. Now, this looks very complicated, but you have here half and third. So we have to look for a certain substitution to resolve this out. So suppose, for example, I take x to the power 1 over 6 is equal to u. Or you can say that x becomes u to the power 6. So you have here dx is equal to 6u to the power 5 du. So that's our substitution. And here you have the integral becomes equal to what? Now, x to the power 1/6 is equal to u. So x to the power 1/2 becomes equal to what? U cube. Whereas, since x to the power 1/6 is equal to u, so this becomes equal to u square. And then you substitute for du, for dx is equal to 6 u to the power 5 du. So see how simple is the integral? So the integral, instead of being so complicated and you don't know how to deal with, have been transformed. And this is the key, as a matter of fact. If I am a student and the instructor, for example, wants me to mark a problem of this sort, so he would give me the most of the mark, I mean a higher mark. He would grade me with I would say 70% of the mark given to being able to find a suitable substitution, because this is the key. This shows how you are smart in choosing a particular substitution. It's not easy to find a substitution, and this is why in most of the exams, what we give the student is a certain substitution to proceed with, and we leave him to see how he will handle the problem. Now this becomes directly equal to what? You divide by u square, so you get here u cube divided by u plus 1. And you have 6 doesn't concern us. And then here, how you proceed? You have u cube. So you divide u cube by u plus 1. Here you have u square. You do a long division. Plus u square. You have minus u square. And then here you have minus u. So you have here minus u square minus u. So you end up again with u. So you have minus 1. Here you have here plus. So it's u. So plus u. And you have here probably when you subtract again, you have u plus 1, so you have minus 1, so you have something like this, minus u plus 1 divided by u plus 1. Something of this sort at the end. And then you wish to integrate this. Of course, the integral is very simple because this one is u cube over 3, this one is u square over 2, and this is u, and this is the logarithm of the function. So although you started with a very cumbersome integral, you ended up with something which is much easier one using a particular substitution. So the key to your problem is this one. Again, suppose for example you have 6 to the power 8 x dx, and you wish to do this integral. What you do, you can do the following. You can transform it into sec to the power x times sec square x dx. And here again, you can, now you have sec square, and we know that the derivative of sec square, the derivative of the tan is sec square. So if you can transform this into a tan function, the problem would be resolved. So what you do, the following. You know that sec square is equal to 1 plus tan square. Tan square x all to the power 3. Because this is sec square times sec square x dx. So now here, we have to search for a certain substitution to resolve your problem. How can you do this? Here, in fact, this is the this is the exact form we have started with, which is the form which is f of g of x times g dash of x. Why? Because what is g? It's the tan. And what is the f? Is 1 plus u square cube. And what is the g dash? Is the sec square. Because since u is equal to tan x, now u dash is equal to sec square x. So if you substitute u is equal to tan, what you get at the end, you get 1 plus u square all cube du. And this is directly is a very simple algebraic integral which you can deal with. And this is how things are done, that you have always to find a certain substitution, and the key is to find a particular substitution in order to proceed. And you don't need to worry about this substitution. The most important thing is that how to proceed later on in order to facilitate your integral and in order to transform it into a form which you can deal with, or you can look it up in a certain text. And as I always remind you, I like to advise you to use the form or the notations of Leibniz, because it's them which always facilitate your solution. So until we meet again, to another form of method, I would say, or procedure to carry on other form of integrals, I wish to remind you that this lesson is uploaded to the site of the Untitled University, and I thank you for your attention again, and until we meet, I wish you good luck.